is everyone doing? Good? So how have you been, during the first class? Everything's going as expected? Everything good? Any interesting observation or like surprise that you didn't know about Moscow? Anybody? What's that? Any fun plans for the weekend? All of you just want to study CHEM101 the whole time? Okay. So I was doing lots of thinking about the ways to have like more class participation and encourage you all. So I was thinking you'll see during the semester, I try my best to have asking you questions and then try to make the class as interactive as possible. I know the previous lecture I was just talking for 15 minutes almost. So I was thinking, if at the end of the semester you're getting 899 or 89 out of 100, and you want to get an A, I'll look at class participation. And you're welcome, so during the lectures I'm going to ask some questions, and especially as we progress, I'll go back and review what we learned. Or I just may ask you a simple question, does anyone know what is an atom? And then you may know, you may not know, or speculate something, guess something. So as long as you participate in the class and you will be active and then have some sort of participation, if you're 2 points short on getting an A or a B, I'll gladly give that to you. And as I said, you are welcome to just email me after the class and say, hey, I answered this question that you asked. But as we progress, during the next session, I'll learn your names, and then I know that, okay, this person always answers my questions, And if you, as I said, if you think that you're not going to participate all the time, or you just participate 1 time or 2 times, and you want to make sure that, hey, no, you're welcome to just email. And as I said, I'll try to be as approachable as possible. So, and I think, you can ask other students too, I think I'm really fast at answering emails. Sometimes when I had students last semester that I was answering, they emailed me 2 p.m. and then I didn't answer till next day, and then after 24 hours they were you didn't answer my email. Because usually I just answer after minutes or few hours. So what I'm telling you, don't be afraid to just send me an email. Okay, so any question about class participation? Okay, and as I said, the attendance is required in the class, but if you're not feeling well, and even if you're doubtful, you don't know what you have, but you wake up in the morning and you have a cough, or you have sore throat, or you're not sure what's going on, just stay home, watch the lecture online, and I have your absence excused. And I also had some students asking me about the book, and as I said, the book is not required. I highly encourage it. And if you have financial difficulty, or you have a certain amount of budget and you really want to have the book, but you cannot, I'll consider reimbursing you. I really want everyone to succeed in this course. And if you can afford to buy a book and you want the book, I ask you to do so, because if I want to do that for all the students, I just get bankrupt and I don't have much money anyway. So, but, as I said, don't, be afraid to just talk with me about things. And I try my best to have really thorough study guides and post everything online. But as I said, I really like to have the book when I was studying, and I think it's really good to have it. So if you want to have the book, but you cannot just talk with me and send me an email and then we figure out the issue. Okay, so now I'm going to start the actual lecture if you guys don't have any questions. Any questions about anything? Everything's crystal clear? Okay, so we want to talk about chemical world. So this is our chapter 1. So when we talk about chemicals, we tend to, I guess it's better to go to here. So your chapter, starts with like sand and water. So in the previous edition, the paper copy of the book that I have, which is like 5th edition, it's talking about soda pop, but it's basically the same. But I'm like trying to be consistent with the 6th edition that you have access to through Canvas. But the materials are basically the same and the concepts are the same. So if you have, like, you consider soda pop, a single drop of soda contains about 1 billion trillion of atoms. And so what are atoms? You can think of atoms as building blocks of materials. So for instance, if you have all the things, all the matter that you encounter with, and then you can see they are made of atoms. And as we progress with the next lectures, I talk more about like atoms and then how they can bond together and what is basically chemical bonding. But in general, now what we learn in this chapter is that all the basically atoms are building block of all materials, and they are really tiny little particles. And atoms are so small, and as I said, for instance, if you consider sand grains, they consist of atoms. And your book, to give you an idea of how small atoms are, it says that if you consider just a grain of sand, that small sand contains so many atoms that the number of those atoms would be more than all the grains of sand in the beach. Does that make sense? So basically atoms are really small and they are building block of all matter. Any question about that? Or like about what is an atom? Okay, and as we progress with the, as I told you, your exams would be multiple choice questions, and most of your homework and quizzes would be the same. And I will post like some sample questions for you so you get familiarized with the structure of the exams. And also in the homework assignments, you see how I ask you these things. But in general, one question that I asked previous semester from students was that, atoms, I said, is the following statement true or false? Atoms are so small that a single drop of soda contains 100 atoms. True or false? Why? Exactly, so this number is really large, and I don't treat you, I don't say like 1 million trillion. I don't say something really close. I don't want you to memorize any number in this course, except like the Avogadro's number. That in the next chapters I'll tell you. But other than that, I just want you to learn the concepts. So as long as you know this number is really large, it's not only 100, you're fine. Or I may tell you that chemicals are necessarily harmful. True or false? What is it? False, right? Because water is a chemical too, but it's not harmful, at least like purified water, that it doesn't have contamination. So as long as you watch a lecture and then study the materials that I post on Canvas, you don't have to worry about anything. But make sure you understand everything. And I emphasize on the basics so much because the previous semester students skipped the first chapters because they thought it was easy, and then from chapter 5 they had serious difficulties. So just make sure that although these things might seem like easy or like not that complicated, make sure to study everything well. The second slide. And as I said, any time that I'm teaching, I have like these specific sections, so you know what I'm talking about. And I'm going to post all the lectures. These slides that you see here, I'll post on Canvas. So you don't have to worry about taking notes and, be distracted. So don't worry about that. But if you want to take notes, you're welcome to. And as I said, I'm going to post the lectures online too. So basically, you don't have anything to worry about. So when we talk about chemicals, usually people tend to think about dangerous materials or like really unhealthy waste materials. So here you can see that, let me have my pointer. So here we have like some sort of like paint materials. As I said, we associate chemicals with like bad smells or like dangerous things. We should have like masks or respirators, or like we should have gloves, This is like the perception we have, or like waste, factory materials, or in general dangerous things. But that's not really the case. When we talk about chemicals, literally anything that you see around you and everything that we touch and interact with, they are made of chemicals. Like, if you have like a pencil, just the tip of the pencil, it has like graphite, and that is basically carbon. Or like water is like H2O, is composed of hydrogen and oxygen atoms. And paper, the same thing, and the sugar that you put in your tea or your coffee or like milk, all the things that you interact with basically are chemicals. Does that make sense? And also, okay, and here we talked about chemicals, and now we want to talk about scientific method and how chemists think. So Greek philosophers, like long back, ancient Greek philosophers, they believed and they would work with reasoning as a way to understand the world. And that is good, but it's not enough. Because in order to understand everything well, we should have a scientific method. And what is scientific method? Here, go back to these slides here. So, scientific method. And scientific method is the method that chemists use to understand the world. So you have like a starting point. So you're sitting at your desk, you're at home or at library, you're just like, you have like your starting point, and you see something, right? Just remember, if you see something, say something. But in general, you have an observation, and it can be, in any aspect of the day in general. But now we're talking about like, scientific method, and mostly in the context of chemistry and experiments, So imagine at this point, you're like in the laboratory, you're like running, an experiment, and you observe something. You can just think about like burning some material or like boiling water or like whatever experiment that you're using. And you'll see really cool experiments in the lab when we start the labs, synthesizing aspirin or like, making hand sanitizer, really cool things, And all of them start with observations, right? And these observations, as we mentioned, they lead to, I guess I just like follow the arrow here. They lead to a hypothesis. So when you see something, you just like assume something, you hypothesize something. And these hypotheses, you should test the hypothesis to see if that is true or not. And when you do the testing, we call that, as we mentioned, experiments. And these experiments can confirm the hypothesis or they may deny it. You know, going back to the boiling example, maybe I hypothesize that water boils at 50 centigrade degree. And you know, we know as a fact that water boils at 100 centigrade degree. So what should I do? I should just like have a, you know, thermometer that is, you know, compatible, you know, to be put in the like boiling water or like really hot water so it won't break. And I should measure the temperature. So I should do experiments to see was that hypothesis, you know, true or not. And then my hypothesis, if I say that, if I was thinking that water boils at 50 centigrade degree, you know, that would be wrong because I do some experiments. And if, you know, we should confirm or revise. So if confirms it, you know, that hypothesis can lead to a scientific theory. And then I, you know, show you the definition and talk about them in a minute. And also, these hypotheses, they also can lead to a scientific law. And then all of these laws and theories, they should be tested again by experiments to confirm or revise. There were like multiple scientists that they had theories about atoms, and they did experiments to see what is the structure of atoms, what do they consist of. And then at the time, they came up with these brilliant theories, and nobody could deny them. But later on, some other scientists, they did like experiments, and they proved that that theory was not entirely correct, or it was incorrect completely. So what I'm saying is that, remember, theories, laws, and hypotheses, all of them should be validated by experiments, and they can be proven wrong. So can anyone tell me what are experiments?
Testing of your hypothesis.
What's that?
Testing of your hypothesis.
Yes, but what are those? If I ask you, I want to run an experiment, what should I do? So what is the definition? But that is right, yes?
Highly controlled observation test.
Yes, so there are like controlled observations. What is a hypothesis? Can anyone remember?
Tentative interpretation or explanation of observation.
Exactly. And some other people here mentioned that too. Yes, so tentative interpretation or explanation of observations, we call those hypotheses. You know, I go back and forth between the slides I have, just like bear with me. So scientific method, and I have, you know, all the definitions that you need to know here. And as I said, I post everything online, so you don't have to worry about, you know, taking notes, just like listen and then absorb all the information. So scientific method, you know, stands in contrast to, you know, Greek philosophies. So Greek philosophers, they used reasoning as a way to understand the world, and the things that I highlight, they are important for your like exams for multiple choice questions. So here, Greek philosophers, they used reason. But the key character, so what is the difference between scientific method and like only reasoning? So in scientific method, we have like some key characteristics. First of all is the formation of hypotheses. And what are hypotheses? So imagine that we see a phenomenon, or we encounter some observation and we're not sure what's happening, you know, or it's kind of like pre-assumptions, if you will. You know, you see some phenomenon and then you're not sure what's happening, so you hypothesize something. It means that you have like a tentative, or you form in your mind a tentative interpretation or explanation of an observation. So imagine you're in the laboratory, and these things, it's good that you learn these concepts first, and then you go to the lab after like 24th of January, you run some experiments, so you learn these things better. So, for instance, you boil some water. I guess for this thing, you don't even have to go to the laboratory. Imagine you have like some water and you're boiling it, right? Now all of us know that what's happening. So water from liquid phase is transforming, or like basically water from liquid phase goes to the vapor phase, right? So water changes from liquid to gas. But imagine if you were doing these experiments years ago when you were a kid. So you had like some water, on the stove, and it was like boiling. And after like 30 minutes, you would come back to it, and then half of the water was gone. So you automatically, I think, humans as like a species, we tend to think of things, right? So you think to yourself that what happened? There were like some water in this pot or pan or whatever you're using, and now half of it is gone. So you think that, okay, one explanation might be someone took it, right? Or some explanation might be that it just disappeared. And actually, there were like, ancient, I think there was like Greek scientists, and there was a theory, we called it Khalwasaya in Farsi, and it was stating that if you have like some rotten meat, or like something that is like being rotten, after like some period of time, bugs or like flies, I think was specifically, would automatically out of nowhere they appear. So it was like some, hypothesis or like theory at the time. Now we know that things, they don't just generate automatically, right? But at the time, that was a hypothesis that led to like theories. So in general, what I'm saying is that hypothesis is a tentative interpretation or explanation of observation. You see something, and then you have a hypothesis in your head. Does that make sense? And as I said, I'm emphasizing on these concepts a lot because last semester, almost like maybe 80% of students, they didn't know these definitions. And they got them wrong in their exams, although I just like emphasized on them a lot during the study guys. Anyway, so as I told you, a good hypothesis is falsifiable. So when going back to the example of water boiling, if you think that water is boiling, and you think that, okay, maybe water just like disappeared by itself, or like if you think that someone took the water, those can be like hypotheses, but they're not necessarily true. And that is fine. Hypothesis, a good hypothesis is falsifiable, which means that future experiments can prove it wrong. And this happens in scientific community all the time. You hear news about like, okay, this medicine can like cure this type of disease. And then after some time they say, oh no, that was false news. It couldn't. So they did some experiments, they went to the laboratory, they did some experiments, and they concluded something, but sometimes scientists forgot there are like other factors contributing to the facts, right? Anyway, so this is also really important, that the good hypothesis is falsifiable, which means that it can be proven wrong. And now we talked about experiments, and you probably heard of experiments, but what is the definition of an experiment? So experiments are highly controlled observations designed to validate or invalidate hypotheses. So if I ask you about, or give you like some lab manual, and I ask you to, perform some experiments. What that means is that you want to observe some, you want to conclude or have some conclusions about something that is happening, and what you should do is to have like controlled observations. And what we do in experiments, imagine you want to see in what temperature water boils, or like after, or imagine you're like boiling water and you don't know anything about like boiling and then phase transformation, you don't know anything. And then you see like bubbles, right? And then you want to see at what point water appears, right? So what you do, you set up some controlled observations or experiments, meaning that at first you have like this stove, temperature really low, like at like 1 or like 2, depending on like your stove setting. And then you see, okay, it took like 1 hour for like 1 milliliter of water. I'm just like making up numbers, right? But you see like it takes like 1 hour. But when you put the heat on maximum or like the stove temperature, it boils after like 10 minutes. So all of these things are like highly controlled observations or experiments. Is that clear? Okay. Does most of you know these things? Are these repetitive or are these new information? How many of you knew what are hypotheses and experiments? Okay, most of you. So this has been pretty boring class for most of you. I guess let me go interesting. So here again are like some definitions that we're giving students lots of headaches. And just remember that there are like different definitions here. And go back here, and here sometimes a number of similar observations lead to a development of a scientific law. And what is scientific law? A brief statement that summarizes past observation and predicts future ones. So for instance, law of conservation of mass is a scientific law. And we're going to talk more about law of conservation of mass, law of conservation of energy, so do not worry about it. But the book included them, so I also wrote them here, and also in the study guide that I'm going to show you momentarily, and I'm going to post on Canvas. So basically, law of conservation of mass states that in a chemical reaction, and I'm talking about chemical reactions later on as well, matter is neither created nor destroyed. And in other words, as we said in that example that I gave earlier, even like when water boils, that can stand for like any, even like physical reactions to, in general, I guess a really simple word is that if I have this pen, this won't disappear. Even, I guess this one, like, I had like also, or if I have like a piece of paper, I may, sometimes we burn things like this, or like, or if I have like a piece of wood and then in the fireplace, I think that's a better example, because I don't think any of us just like burn things for no reason. But if you have like a fireplace and then you have like some wood in it and then you burn it, after like, after some time, you may not see the wood sticks anymore, but they didn't disappear. They now became ashes, right? So they burned, they changed from one sort of material, like wood, to some other sort of material, ashes, and we're going to talk in more detail about those. Or if you like boil water from like liquid phase now converted or changed to water in gas phase, right? So you have like humidity in the air, but that didn't disappear. So that is basically law of conservation of mass. that matter is not created nor destroyed. You may not see it anymore, right? If you have like acetone in liquid phase here, and then you know that it's highly volatile. After some time, you may not see that anymore, but it doesn't mean that they don't, they just disappear, right? Any question about that? So, can anyone tell me what is a scientific law and give me an example of a scientific law? Anyone? You can just read from the board too. Scientific law, anyone? Yes.
A brief statement that summarizes past observations and predicts future ones.
Mm-hmm.
And the law of conservation of mass is a scientific law.
Exactly. So imagine that burning example that I gave you, right? We have some fireplace, just imagine that we have a fireplace and then I have some wood there, right? And then after 5 hours, then I have a small stick, right? And I'm just making up all the numbers. After 5 hours, I don't see any wood anymore, but I see some ashes, right? And I go to the laboratory, take some sample, and then examine to see exactly what I have, right? And then if I do the experiment, some other time with some other material or some observations, and then every time I see the same material is generated. So now I just call them ash for the sake of simplicity. But if I just, every time that I burn wood, I see the same ash, now I can come up with a scientific law that, okay, when every time that I burn this, ash will be generated, and now I can predict, that if anyone else gives me some other sort of wood, still the same thing would happen. So you have some observations, right? And that can lead to a scientific law, and that also may help you or will help you to predict future observations of the similar nature. Does that make sense? Okay, now can anyone else tell me what is a scientific law? So this is an easy lecture, this session, so I'm just going to ask several times so all of you participate. So can anyone tell me?
Gravity.
So what about gravity?
It's always works. You're not just gonna fall off one day.
Yeah, that is an example. Yes.
Is if an object in motion must stay in motion, is that a scientific law?
That can be, yeah. So scientific laws, they should be, so it should be well established, and then so what I'm saying is that, I guess the examples that I gave, they can lead to a scientific law, but it might not necessarily formulated in literature. Does that make sense? But in general, yeah, if you have several observations, and then you come up with the conclusion or a law in your head, and then based on that you can predict future observations as well, that can be a scientific law. Okay, can anyone tell me the definition of scientific law? And as I said, the reason I'm emphasizing because I want all of you, when I say that, sometimes a similar number of observations can lead to the development blank, I say that is a brief statement that summarizes past observation and predicts future ones. Which one of the following is that? Scientific law, hypothesis, theories? I want all of you to answer the question right. So can anyone tell me the definition of scientific law?
A brief statement that summarizes past observations and predicts future ones.
Exactly. Is that clear to everyone? Any question about that? Okay. So we talked about also law of conservation of mass, and we're going to talk about that more in the next chapters too. Now, one or more well-established hypotheses may also be the basis of scientific theory. So now, theories are similar to scientific laws, but they provide broader and deeper explanation for observations and laws. So, scientific theories are also called models. And the reason that I wrote this here is that almost everyone last semester got this question wrong. I was like, what is the other name of scientific theories? And I was saying scientific law, hypothesis, experiments, models, and almost everyone got it wrong. So remember, scientific theories are also called models. So, we even use these words like hypothesis, experiments, like theory, even we use them in their daily life too, right? Sometimes you see something and you say, okay, I have a theory in my mind. That is, why it happened. So theory not only is, so it's similar to the scientific law in a sense that, when you have that is, summarizes past observations, they have this similarity, but the theories, they provide deeper explanation to why things happen. So it's not like just saying, okay, this is how things happen, also giving more explanation. Does that make sense? So this is the difference. And we also call them models that, kind of like a really good example can be the atomic theory of John Dalton, and we're going to talk more about that in the next slides. So theories are models of the way nature is, and they often predict behavior that extends well beyond the observations and laws on which they are founded. So this is the difference between scientific law and theories, that they provide deeper explanation. What is the other name of models?
Scientific theory.
Perfect. Now you want to prove we're better. We know this. So a good example of a theory is the atomic theory of John Dalton. So as we mentioned, atoms are like building blocks of all the matter that we encounter, and Dalton was saying that all matter composed of atoms and they are indestructible, meaning that if we have an atom, we cannot divide it to smaller constituents. And as we see in the next chapter, that is wrong. And atoms themselves consist of different particles. So, and that is the thing that we mean by, they are falsifiable. Both all theories or like laws, hypotheses, all of them may be proven wrong. And you see that in literature, previously there were like lots of things, or like a good example is like smoking, At some point, companies were denying that smoking cigarettes can cause lung cancer. And now it's like well established that that's not the case. So even like scientists can be wrong. And just remember that all of them are like falsifiable, even like theories or scientific laws. Theories are also tested and validated by experiments. We just mentioned that. And as we mentioned, scientific method begins with observation. And then laws, hypotheses, and theories are developed based on observation, as we saw in the previous PowerPoint or like slide. Experiments, which are carefully controlled observations, determine the validity of laws, hypotheses, or theories. So now I expect you to know the definition of hypothesis, experiments, laws, series models and knowing that all of them are falsifiable. Are we good? Any questions about anything? Okay. So now, section 1.4 talks about analyzing and interpreting results. So we usually, when we want to analyze results, it's more efficient for us to put them in a table or in a graph. And most of the time, scientists prefer graphs because you don't have to just like look at the numbers individually. You can just look at the graph and like make a, conclusion based on the data. So here, you see that when we want to analyze when we want to read the graphs, is it like, do you all know that how to read this graph? For instance, if I ask you, what is the concentration of carbon dioxide in the year 1940? Right, so here. So what is this amount? How much is it? Yeah. So basically you go here, find this point, and then you read the equivalent number here. So it's between 300 and 320, so it would be 310. Any question about reading the graph? And now here we have like a sample A, B, C, and then we have mass of water in each sample. So now you can read this data that, okay, here, depending on how you read the data, and then you have like, and in your book you can have like more, thorough explanation about like what are these graphs, what do they represent. But here I just want to show you how these things work. So okay, resume. Okay, just accidentally paused the video. So we have like water that transforms to like hydrogen and oxygen. So you see that in the first sample we have like 20 gram, and then it converts to like 2.2 gram and like 17.8 gram. As you can see, if you add these two numbers, 2.2 plus 17.8, what would be the answer? Exactly, and it shows a law of conservation of mass, right? And then if you have like 50 gram, you will be having like the same thing. If you add these two numbers, it would be like 50 gram. And then the same for like 100. So based on these observations, you can see that, okay, matter is not destroyed. So you can come up or like validate the law of conservation of mass. Does that make sense? So this is how you should read the graphs and tables. And lastly, a beginner chemist, how to succeed. Before I do the attendance, I want to talk about how you should succeed in this course. So your book had like these cute images that in order to succeed, you should be as curious as a child. You see that sometimes children that just like ask why several times. Why is it like this? Why should I go to school? Why should I, just like whys. So anything that you see, and then you read, you should be curious. And this is a scientific mind, that why things happen. And so first, let me do some attendance and call some of you guys' names. Okay. Is Brandon here? Oh, like? Okay. Dane? Frankie?
Here.
Joseph? It happened for my previous class too. I knew there were lots of students absent, but anyone that I call randomly, they are present. That's interesting. Ethan?
Sure.
Sydney? Sydney? Sydney's not here? Daisy? Yes. Miranda? Where? Oh. Haiti? Haiti? Myers? Yeah. Alright. Danielle? You can just also, raise your hands, regardless of last name, like just like you said later. Danielle?
Daniel?
Yes. Alex? Lou?
Yeah.
Where?
Which one?
Fran?
Oh, no.
Okay. So what's your last name? Okay. Natalie? Ella? Hayden? Okay, that's fine. We'll just put 2 things. John? Luke? Luke?
Yeah, that'd be me.
What's that?
That'd be me.
Okay. Noah? And I apologize if I pronouncing your names incorrectly, just like correct me, like your friend did. Kimberly? Anna? Avery? Okay. Holden? Yeah, and as you can see, I just do that randomly each session because in our undergrad, professors, when they wanted to do attendance, they would just give us piece of paper to write our names. And sometimes the students just like write their friends' names. And sometimes, students become stressed to write their name and they're not listening to the lecture. They come to the class a couple of minutes late. So I just randomly do that. So, and if I don't call your name, you're good. So don't worry about it. So, see you.